Hello everyone, welcome to the tutorial on LLMs. This is Devarpan. I am a PhD student at IISc Bangalore. Today we will be covering a tutorial and associated demo corresponding to the large language models. It might have been covered in the course mostly from the theoretical side and how LLM is built. Today we will show some working examples and multiple aspects of large language models, specifically different components that make a LLM together finally, and touch upon those different parts and analyze them. So hopefully you will get an overall picture about how a LLM is built. That is the purpose of this tutorial. Let's start with the session. So first of all, the most common thing you might have come across LLMs is probably using ChatGPT. So you give any question, it's able to answer, right? So it's about what's most interesting and surprising about it is it can answer questions from across domains. So it has that foundational capability so that it can generalize across domains and has expertise in multitude of domains. So let's start with that itself. So we'll consider questions across domains like arithmetic, science, general knowledge, simple reasoning, and programming concept. Let's see how a LLM is typically used, and they are so generic that it can question and answer questions across all the domains. So we first install all the dependencies, libraries like torch and transformers, and then import them, and we load the define the model name, which is Mistral 7 billion, which is a one of the widely used LLMs, and then you can you have to define the tokenizer from that for that particular model, and add the padding token, and then you need to call the model, right? Call the model so that it's ready for the inference, and you have to do the processing in GPUs. So you have to define the device equal to CUDA, and call the model equal to eval model.eval, so that the gradients don't pass and the GPU usage is limited. So that's about making it ready for inferences. So coming to creating a then we call a function called answer question, whose job is to given a prompt and max number of output tokens, it simply returns you the response. Now coming to the questions, we define couple of questions from the domains that we have talked about. For example, from math, what is 27 plus 45, for example, and then from science, does the boiling point of water increase or decrease at high altitude compared to sea level, right? And then from something from geography, what is the capital city of Japan? And then from history, who was the first person to walk on the moon? And coming to programming or computer science questions, in programming, what does the acronym CPU stand for? And in Python, what keyword is used to define a function? And for reasoning type of questions, if you put ice cubes in a glass of warm water and wait, what will happen to the temperature of the water? And also, like, you leave your umbrella at home and it starts raining while you are outside, what is the most likely consequence, right? So given this question, let's see how it answers. We simply create a utility function and iterate over all these questions and make the model predict. So how do you evaluate if the predicted answer is correct? So we have the ground truth answers. We compare them using rogue score, which is a lexical matching metric to match different answers which might be matching but lexically little different. So rogue score essentially matches them irrespective of slight lexical variations. So we found that it only make wrong prediction for the one of the math questions. However, it gets all other right. leading to a score of 9 out of 10. So you can see across such diverse domains like history, geography, math, reasoning, it performs really nicely and getting 9 out of 10 correct. So this is just a starting example of how LLMs, such a small LLM itself is diverse across domains and have expertise and knowledge across domains. That's the such a good point about LLM. Now we'll slowly dive into the inner details, like what are the basic building blocks of a LLM and its utility functions, its output sampling, and so forth. So we start with the masked language modeling. So masked language modeling, you might have seen in the courses itself, because that might have been covered in the course in a more detail. But masked language modeling essentially is the core building component of the LLMs. When the pre-training of LLMs happen, they are essentially trained using masked language modeling as the objective. In this, some words and subwords are masked in the training corpus, and then the model is told to predict it, right? So we simply take some masked language models from Google, which is like BART, and show you that how nicely it can predict the masked regions. So we load the BART model. After that, we create this function so that it outputs the prediction. Given a sentence, some masked region, it should be able to predict what was masked. For example, we take this example, the capital of France is, and then use the mask. And you have to show the predictions of this masked language models BART. What are the top 5 probabilities that some word comes here? So the top 5 probabilities are Paris with probability 0.4, and that you can see that other words are not correct. So Paris gets it right with a very high probability as compared to the other words. And then if you do a generic, ask a generic sentence like deep learning models are very, and then mask. So top 8 predictions are like deep learning models are very simple, deep learning models are very popular, deep learning models are very common, deep learning models are very effective, deep learning models are very different, complex, useful, important. You can see that the top few words are fitting better as compared to the words towards the bottom of the list. And then if you have a few examples like the weather today is very masked. The neural networks can be difficult to mask. The ISC is a masked institute in India. So you can see for the first case, the weather today is very warm, good, hot, pleasant, cold, like all of them fit very nicely, and you can see the probabilities are also close. And for the example, neural network can be difficult to understand, study, analyze, predict, construct. So they also make up pretty fairly close probabilities. And also for the sentence, ISC is a mask institute in India. So the mask corresponds to research, medical, management, technical, technological, right? Maybe the medical is not so good fit, management is not a very good fit, probably the technical and technological could have come above medical and management, right? So you can see they are not again perfect. But when you do this practice on a huge large corpus of the data, so often the community says that the entire data available in the internet was used to train cutting edge LLMs like ChatGPT and others. So this masked language modeling, once it happens on such huge corpus of the data, it learns to do inherent semantics, and it becomes so good that it acquires knowledge across domains like that. So let's move on to the next token prediction part. So masked language modeling, you are seeing that the mask can be put at any place in the sentence. However, if you do that in causal manner, like mask is only put at the last. So given a already sequence of words, you have to predict the next word, right? That's how these GPT style models are trained. They are called, that's why decoder only models. So we'll first load a pre-trained GPT-2 model, which is open sourced, and then inspect the next token probability distribution for a prompt, and then generate a short continuation using sampling. So we load the GPT-2 model here using CUDA, and then so the theory of transformers in deep learning, that is the prompt, and it has to predict the word that comes after that sentence. You can see is probably the most probable word, and then others don't fit that way. So is has a larger probability of 0.3 to 1 as compared to others. Similarly, you can set other parameters like how many output words or tokens you want maximum, and then if you want to do stochastic sampling where when you are decoding the word, and then how many top predictions you want to take among this list, like here k equal to 10, right? So like that you want to consider a list of top 50 predictions, and you can set the temperature. Temperature is something which controls the stochasticity when you are sampling the outputs. When you are sampling the output, if the temperature is high, you get more stochastic and random predictions with lot of variations. If temperature is low, it becomes sharp and always tends to predict the most probable prediction or top one prediction. Right. So this model was put free flow. So after it predicts the first token, then it becomes let's say we pick is, then the prompt becomes the theory of transformers in deep learning is, then the next word has to be predicted again, right? Like that, if you go auto-regressively, it predicts something like this. The theory of transformers in deep learning is based on the work of David G. Lipsner, 1977, who has shown that the number of possible directions in an axial plane is limited by the number of possible values in the x-axis. Like that it can, so after that, in the case of simple, it simply stops because you have given this maximum output tokens to be 50. What is a token? I will come to that. That's a very precise statement. Right, so you can go on like this. We have created couple of more examples, you can read them. So it can essentially generate long paragraphs, sentences, and even stories like that when this is scaled up, trained with a lot of large amount of data. It can essentially generate such stories and complete sentences, expand some writing, and so on, like whatever application you also typically do, I'm sure, with GPT, and those are very much scaled version of this. Now let's come to the, so you have understood how masked language modeling works, which is the core of it. Now let's come to how exactly words and text data is processed while training these large language models. The theory part of the course might have covered the byte pair encoding and tokenization a bit. So just let me summarize once more and recap that tokens are essentially words or subwords that form the basic units of a language. So when you have effective tokenization and you break words into subwords, then you start to have repetition of the same words across different words and sentences. That makes number of possible tokens to be limited, whereas if you only relied on the words, then there can be n number of different words and you will always encounter some unique word which is not there in your list, and the vocabulary size will grow exponentially, whereas relying on token limits the number of possibilities. So for example, let's see, we'll analyze tokens broken down from words and sentences by different models using this function show tokens. It does this. So tokenizer dot tokenize, given the text, create the tokens. We will look at how it is breaking. Different models are breaking these sentences. We took 4 different sentences. Internationalization is often abbreviated as I-18N. IISc is a premier research institute in India. ChatGPT is a large language model. Not communicable diseases are a major health concern. Let's see the tokens that GPT-2 and BART creates from these sentences given as input. So GPT-2 tokenizer works like this. it takes international as a single token, then ISIN as another token, is often like that. It breaks this sentence into different set of tokens. BART tokenizer also does similar kind of things, very similar kind of things. So here if you look at, IISc is a premier research institute in India. However, the tokens that the BART and GPT-2 create are little different. GPT-2 tokens I and IS and C as different tokens, whereas BART takes IEI and SC as different tokens from ISC. Like that, there will be different variations for these different models, but what you can understand is that all the models try to tokenize in a way that they create subwords which will be repeated for other sentences and paragraphs as well. So it becomes a very generalized set of tokens. Other examples also you can go through. And if you only focus on words like different kinds of word, one Hindi word, Antarashtriya, IISc, Bengaluru, non-commutativity and internationalization, and if you try to break them into tokens, you can look at how different models are breaking them into sentences. Essentially, for the Hindi word also, they try to break it into different tokens so that so BART essentially breaks it into different simple one alphabet in Hindi. So it's breaking it like that, but GPT-2 is trying to at least make some combinations of the different alphabets. We have already seen GPT-2 and BART breaks IISc in different set of tokens. Something interesting happens for Bengaluru. So the tokens are B, ENG, AL and URU. So that GPT-2 breaks it into. So you can see you will repeat, B will come again in lot of words in general. ENG is a very common phrase or subword which will be repeated across different sentences. AL is also something like that. So it's trying to break it into commonly repeating subwords that combine differently to give rise to different words. However, BART does it in a different way. It breaks it into Bengal and URU. So Bengal is again a subword which will be repeated in different contexts. Like Bengal itself is a state. Bengal will be coming in the word Bengali also. So they cover a lot of words and sentences and make it generic. So let's now slowly move on to sampling and temperature in LLM decoding. What we will be showing is how different decoding strategies affect the text that is getting generated by these causal language models. So what we will compare is essentially greedy decoding, which has no randomness, then temperature sampling, then top K sampling and top P sampling. First, let's start with greedy decoding. So in greedy decoding, what happens is that temperature is set to 0 and sampling is set to false. Essentially, setting sampling equal to false is enough, and when you don't want to sample, then always the model outputs the highest probability token that it is observing. It doesn't sample from that output distribution. It always outputs the top one prediction that it is getting from that probability space. That's why it's greedy, right? That's why it is called greedy decoding. So we load the GPT-2 model again in the similar fashion. Now we want to generate output given some settings, like what is the maximum number of output tokens if you want to sample. So if you said do sample equal to false, then the greedy output will come. Then what is the temperature you want? So temperature is relevant when you say only when you said do sample equal to true. Otherwise temperature doesn't matter. Temperature controls the randomness using which the sampling will be done. And then top K and then top P. Inputs, then first the input is tokenized, and then using top P and top K parameters, finally the output IDs are obtained, and then if you do tokenize.decode, it returns the output text. So we start with an example. The prompt is transformers have changed natural language processing because, and you want the sentence to be completed. In greedy decoding sense, it will always pick tokens with highest probability. So first it will pick the token that comes after because with highest probability, and then after that it will give in all these tokens. What is the next probable token? It will pick that with again highest probability. Like that, the decoding will keep happening, and in the the sentence you obtained in that greedy decoding fashion is transformers have changed natural language processing because of the use of the new language. The new language is called language specific and is used to describe the language of the language. The new language is called language, like that. It is just completing it. However, if you set the temperature to be 1 and you have to set do sample equal to true as I told, then you get something like this. Transformers have changed natural language processing because they have used more advanced information about the source language. These include the ability to write a custom code base that does a much better job than simple bytecode that simply replaces the source language with the language. So you somewhat get a more semantic output here. So introducing the randomness essentially cancels out some noise in the predictions and sometimes can give diverse outputs, which in different cases you will want. So what is the effect of temperature can also be studied. So you can set different temperatures 0.3 till 1.5 and you get the predictions out of it. If you see, if temperature goes very high, then sometimes it may get very noisy. Like large language models are useful because they represent a language independent language on a single input output system such as a graphical application, and also facilitate a very generalization of current system and development protocols in the form of programming. Yeah, somewhat sensical, but if you keep increasing it, it will become so noisy that it will not make sense so much, right? Okay. Now comes top K sampling. So if you remember, we are always considering the set of tokens that are getting predicted in a list of 5 or 10, right? And if you would want to limit that size to a specific number, like you want to consider only top 8 or top 5 and then some sample from that, and you don't want to consider the very low probability tokens that is coming at the bottom of the list, maybe after like top 50 or top 30 or top 20, there will be a lot of tokens which are close to 0 probability, you would not want to consider them while sampling. Then you can say top K. Top K sets the top few entries in the list and then sample from there. So you can vary the K essentially in 5, 20 and 50 and then do the decoding, right? And you can see how the output is changing. Similarly, you can do the top P sampling as well. In top P sampling, what happens is that the first, let's say the first one in the list, the top probable, the greedy token essentially, top probability token, that has a probability of 0.5. Now the next one has a probability of, let's say, 0.3, and the third one has a probability of 0.1, and the fourth one has 0.05, and so on and so forth. So if you want to limit based on the probabilities, top probability, and rather not size, because let's say if you want to consider only top 5 always, the top 5 total probability, sometimes it will be only 0.5, sometimes it will be close to 0.9. If you don't want to do that, you want to rather say I want to consider token which have considerable amount of probability in it, then you have to use top P. Then you can say like I want a 90% probability, accumulative probability tokens only. Then for cases when the top 5 tokens probabilities sum up to 0.9, effectively top K equal to 5 is getting used. When let's say top 10 tokens sums up the probability to give you 0.9, then it's like well distributed, then you will automatically consider the top 10. So it's a variable top k it becomes based on the equalization of the probability. So you can set what is the total accumulative probability you want to consider from the top, like you want only total 30% probability token, 70%, 90%, typically it's set to 90%, and you can sample using that. Now we come to the part of post training, which consists of supervised fine tuning and alignment. So the supervised fine tuning happens with LoRa because LLM has a lot of parameters, and there is a very nice paper called low rank adaptation. You should read it. So what they find essentially is that the weight matrices that the LLM have, they find the low rank approximation of that using a rank parameter, and they update the LLM's weights corresponding to that low rank approximations. So the GPU usage that you need to update the model during a fine tuning becomes very less, typically only 1%. So even a small GPU can fine tune such large LLMs of 7 billion, 8 billion and others. So we'll show us minimal supervised fine tuning loop using LoRa, and we'll show like how the model behavior changes before the fine tuning and after the fine tuning. We take GPT-2 again, and we essentially you have to create a data set where there will be a lot of instructions and responses, and it is called instruction tuning. Then you have to format your example and then create your data set. Once the data set is created, you have to create that training configuration. So LoRa configuration, you have to make a rank and other few hyperparameters that are associated with LoRa, and then you have to load your model, and it's now ready for training or fine tuning. So after the tokenized data set is created, you have to create the train data loader and the optimizer, and you can call the model ready for training. So by calling model.train, and for multiple epochs that you have, you can print the loss and keep training it. This is just a very simple demonstration. So of course with this 5 or 6 set of responses fine tuning data sets, you can't expect a model to learn anything. But given a very large corpus of this fine tuning data set, you can using this similar setup and little bit of extension of it, you can fine tune essentially any LLM using a small GPU, and it will be able to learn the new task that is associated with the fine tuning data set, right? And yeah, you get the generated answer, right? So the fine tuned model gives a prediction that it's different from the initial prediction that it was making, but to make it essentially effective, you have to do this exercise in a much larger scale of the fine tuning data set. Now we come to preference modeling and direct preference optimization. This was also I think covered in the course. So the LLMs are making some outputs, but they might not be aligned with human values and human expectations. So how do we align these LLMs prediction so that it's aligned with human values, sense of safety, sense of expectations, the politeness, right? It's not about getting just politically correct. It's also about being gentle, polite, and then not making toxic comments, not insulting people. Such human values should be incorporated in LLMs to make it usable for daily use by humans, right? And you might have seen for GPT that it always gives prediction which kind of satisfies your expectation of the way of answering that it has. It's not just crude, right? How is these things incorporated? Is using something called reinforcement learning using human feedback, RLHF, and how it is trained is like direct preference optimization using reinforcement learning. So you essentially create a set of preference data where given a prompt, given a question, expect what a large language model is. So there can be two answers. A large language model is a neural network trained on massive text data to predict and generate text, enabling it to perform many language tasks. And another response could have been maybe the LLM itself makes another prediction saying that a large language model is a small database of a few sentences. So which is wrong. So it's even if it was correct, the first one is both correct and very nice prediction. So a human is sitting and he is giving the feedback that okay, this first response is preferred over the other, so this is chosen, this is rejected, like that. How would an AI assistant respond when it does not know something? It would, the possible two responses the LLM makes are, it should say it is unsure or cannot answer and avoid making of facts, or it should confidently guess an answer even if it might be wrong. So of course you would prefer the first one, like this is chosen and this is rejected. Another example, explain supervised fine tuning. Supervised fine tuning adapts a pre-trained model on labeled input output examples for specific tasks. Another can be supervised fine tuning is random training without labeled data. So of course second one is not correct. So first one is chosen, second one is rejected. So there is a human feedback involved in this, and among multiple alternate responses a human prefers particular response over others, and that is used in a reward model in an enforcement learning setting to train the model, right? And that's how this post training happens. So we create this preference data set that we have already talked about, make it ready for training, and also create a reward model based on the chosen and rejected responses. Then you set the optimizer and loss function, then the training can go on. You set the model to train mode. For number of epochs you keep on repeating the training process, and finally in the evaluation mode you can see, like, given a so you can see that it often what are the score that the new model puts for the chosen response and rejected response. You can see that it always gives a higher score for the chosen response, like minus 4.02 over, which is more than minus 4.05 and all. So the same thing for the other example. So this is very minuscule experiment, but when you have a really large corpus of such data set and you do this training for a large number of epochs in a large batch size, then the model automatically learns to align its response based on the human preferences using this reward model. That's why you in GPT you see that it always predicts something that kind of, it's very polite, is how we would converse with another human being with utmost respect and care, and civilized manner of speaking. It has all of that. That's because through this reward based post training these human values are incorporated in it. Finally we come to a model called in context learning. I think that was also rigorously covered in the course. So what, just a quick recap, what is in context learning? Let's say you have a LLM which is trained on some task, but you have a new subtask that is not exactly same as the training task, but it's related, right? But now you want the model to be capable of performing this new subtask also, which is not exactly same as the training task. So then you have to either fully fine tune on the new task, like we have talked about supervised fine tuning, that you have to do that, take that new data set and fine tune your model. Another possibility is train the LLM from scratch itself, combine the training dataset and that new subtask dataset and then train the LLM from scratch. So both involves, although the first one is worse, first one is better over the second one, like you can only fine tune keeping the previous knowledge same, but it still involves a long training process using GPUs and a lot of resources required, a long dataset is required and so on. Often people, what they have found is, like, at least in this in context learning setup, you can give couple of examples from the new setup, as long as the new subtask is related to the training objective. From the examples itself, the model can pick up the new task and answer a question which you are putting at the inference stage without any weight update. So when you give couple of example and ask the question, there is no model update happening, but in context it's able to learn this new capability. We'll show one example. We load a small model called Coin 2.5, just 3 billions, very small model, and then you just tell to generate the response in a greedy decoding mode. That's it. Now let's come to the example. So we have a number called 18, just an integer 18, okay, and the LLM is trained on a lot of world knowledge, right? But what you would want to, so you define a new subtask that you want to label all odd numbers as foo, and all the even numbers, all the even numbers as foo, and all the odd numbers as bar, right? But the LLM doesn't know that. So you want to create a lot of odd numbers and even numbers, label them using foo and bar, and then do the supervised fine tuning of the model. Then the model will be able to say it. But that is such a rigorous process. What's so great about in context learning is that you can only give couple of examples of odd and even numbers and label it as foo and bar, and without any fine tuning, just given in the prompt as in context, it will be able to learn that mapping. For example, we create this prompt. You must label each number as either foo or bar. Here are some examples. So you create a lot of examples of even and odd numbers with the labels foo and bar. For example, number 2 foo, 4 foo, 6 foo, 8 foo, 7 bar, 12 foo, 11 bar, 14 foo, 13 bar, 17 bar. Then what should be there for the number 18, right? So you have not made any consecutive numbering and all that. Foo and bars are not coming in an alternate manner, right? But the only thing it has to figure out is that this is even number. So when you first do zero sort meaning you only ask this question without giving the in context examples, and in context is like you give these few short examples and then ask the model to give its prediction. What it does is that when it was zero sort, it says bar, but bar was always, we want the even numbers to be foo, right? But it doesn't know that, so zero sort has no way to predict it. Whereas you want the model to learn the task in context without any fine tuning, that same zero sort LLM itself. So you once you give this example in context, it's able to answer bar. It's able to answer foo, right, correctly. So it has learned this new task through these examples itself. That's so strong about in context learning, because you needed no fine tuning, no training procedure, and just giving the in context examples in the prompt, it's able to learn this new task. So that's about it for the tutorial and both in context learning. I think what we have tried to cover is to give you minuscule example and basic concept around different components that the LLM has, and hopefully that was helpful in building up your confidence around the theories that you have learned in the course that the instructor has covered. And hopefully I have not tried to go to a lot of rigorous implementations, rather try to focus on give you some head starts on the implementation, so that you can any specific one you can go deeper. And I have tried to cover rather all the topics that are the most interesting and widely used even in research and so forth. These different components I have tried to touch, so that whichever is more interesting to you, you can dive deeper into it. And I also have given you starter codes to understand the concepts. Hopefully that was helpful. You can run this notebook in a Google Colab itself, so a quick implementation and head start for you again as well, without any cell phone GPUs and others. So this notebook will be available, I think, through the course, and you can use it as it is and make further experimentations on it. Hope that was helpful, and thank you.